Hello explorers and welcome to another video. Today we're going to do some machine learning and we're going to go all the way from Java, creating our data set, from custom images, all the way to a JavaScript library in order to use it on our web page. So in this case here I have a bunch of cats, and the first cat here is correct, it's a cat. The rest of them are dogs. So it didn't really figure those ones out, but the dogs are spot on. It can figure all the dogs out. So this I trained for about a day. It got to, I think, 70 in accuracy. I did have a very limited data set of about 25,000 images. So with a better data set and a little bit more training, perhaps a better model, we could do even better than this. But I think the important part here is the actual setup and how we use the framework, and the other things you can fine-tune to your content until you actually get something that works for you. So let's look at the code here. First off, I use Maven, so I have some Maven dependency here. I need to have TensorFlow as a dependency. I need to have TensorFlow Proto, so protobufs. I also use common codecs, and I use the TensorFlow lib directory. And I use TensorFlow Hadoop. And Hadoop I use because I want the writer in order to write down the result from my dataset. So I take everything that is in example, TensorFlow example, so I can create examples. And then I take the TFRecord writer from the Hadoop utilities library here. And also in protobuf I have byte strings, I can use those. So I have this function that is Runfile that I will use in order to create something from a file. So let's close some of these down here. So we start with the main function. We create a file output stream to TFRecords. It's a data output stream, and we put that into our TFRecord writer. So that's how we create this writer that will write our TFRecords file. And then I open the directory of pet images. So I have 25,000 images of pets, either dogs or cats. And then I have this label 1. And it also always starts on the first directory, and that's the cat directory. So that's label 1. It will go through that directory for all of the files and run those files through this run file. And when it's done with that directory, it will update the label to 2, so dogs are 2, and then run through the dog directory and input all of those samples as well. So let's go over to run file here. When we run a file, we first off create a buffered image here. We will read the image from the file, so we actually have the image to work with. If the image is corrupted in any way, we'll throw that away. We will get the height and width of the image and the depth. And all of the images I create will be RGB, so they will have a depth of 3. So then I will put that into my record here. So I will put in int values here, so int feature, and it actually creates an int64 list of features and then put that into our data pool here. So I will put in int features with width, height, depth, and the label. So all of those I will create first, and then I will put in a string version of the raw image data. So if we look at the feature here, it will actually give you back a feature, but it's a string feature. So first up we take our image and we will create a new image from that. We will create a graphic, and this new image is of type RGB. And then we'll create a graphics object. We'll draw our image into that RGB image. After that, we will create a byte output stream. We'll write our image to that byte output stream, flush that out, and then take all the bytes from that stream and copy it out to a byte stream. So this is a protobuf thing. And then we will close the byte stream and we'll create a bytes list. So this is the string feature that we will create. It's called a byte list in this case. And then we will put that in. And when we actually get it back, it will be a string tensor when we read it back from the TFRecords file. So this is the feature we'll create here and get that back. And that we'll put as image raw in our TFRecord file. And we'll go through and create example after example and just write them out to a file. And that will give us a file of a size around 600 megs. And that is what we will train later on. So let's go over to the training code here. First off, we had some functions up here. So I think I will take those as they come. So first off here I have this data record set that will read a TFRecord data set, and it takes a bunch of file names, and I found this nifty function online that will traverse a directory and give me a list of all the files in that directory. So this is the function up here. So this is something that I copied from an example online. I don't use it at the moment, but it's quite nice to just have something like that, because then I can actually create multiple TFRecord files and read all of them as a list and use all of the training data from all of these files. So I don't need to create all of the examples in one go. I can do it incrementally as I find more examples to work with. But in this case, I have this new data set that I called pet images 2 TFRecords, and that's the one I want to read in now. So I just used that file for this example. And then I will read that in using this parse data set, and I will map it with the TFParse function. I will shuffle it up, and I will shuffle the buffer size of 50,000 records. I know that I have much fewer than 50,000 records. I only have 2,500 or 25,000, but at least I know I will read all of them before I shuffle them, so I will get a good mix of them. Let's look at this TFParse function. It's pretty much this function up here. We will set which features we have. We have the width, the height, the depth, and the label. Those are all int64 features. And then we have this image raw, which is a string feature. And all of those are lists. So we will read them in as lists here. Then we will parse this example here by getting the record of the current new axis. And we uses these features. With this parse function, we will actually get the data back here as tensors. And then we will go through here and decode the JPEG here. And that's the first instance in the array of image raw. We will decode that with 3 channels. And then we will reshape it with the width and height and depth. So we have all of the data here. After we have done that, we will actually change the width and height of it. So I have a set width and height here of 300. So we use this function that will either crop or pad the size of the image in order to create a new image that is in the new dimension. So this will give me pretty good image that I could actually train with. If you want a really good result, then try to do this beforehand when you create your data sets. You go through your image set and actually create images of the same size, and that will improve your training. So if you do a lot of work beforehand on your data sets, you get good training sets, then you also will get a better result afterwards. And then I will get the label as well as this int64 and get that out. and I will return the image and the label. If I didn't want to use batches, I will return image and labels as arrays here, because I need a dimension that is an array of at least one item. But if you batch something up, it will create this array for you. And that we will see down here. So I actually take a validation data set here from my parse data set, and I will take the first 1024 images, and I will batch those up in batches of 16 images. And if I get too few images, I will actually drop the remainder of the images in order to just get a full data set or not. So if I don't get 16 images in my batching, then I will drop the rest. The same goes for the training set, but I will skip the first 1024 because I don't want to use the validation dataset when I have my training dataset. So the training dataset I will train on, and then I will validate that against my validation dataset. Then I will create a sequential model. So I have added up here from TensorflowJS models, I have sequential models, and then I have some different parts of the network, so convolutions, max pooling, activations, dropouts, and so on. And I will also use TensorFlow and TensorflowJS as libraries up here. So if we go back down here, so I will first create a convolution of kernel size of 3, and I will create 32 layers of that. And I will use relo as an activation function, and I give it the input shape of the width and height and channels 3 here. And keep in mind that you also always put the height first and the width second when you're working with your model here. So you swap those around from how you usually read an image. And then we have the max pooling. I will do a max pooling of 2 here, and then I will do batch normalization. So this is pretty much a network that I found as an example online, and it performed pretty well. If you fine-tune this, you can find a model that does even better than this. Then I have 64 layers and max pooling and batch normalize, another equal layer again. Then we have a 96 layers convolution, same activation function and so on, and then 32 again. And after that I will flatten my model. I will create a full layer here, a dense layer of 128. I will have a dropout layer of 0.2, so I will drop some of that so I don't overfit. And I will use a dense layer again here of 3 because my output will be either 1 for cat, 2 for dog, or 0 for none of them. So this is the activation layer of 3 different classes. I will use an Adam optimizer. I really like the Adam optimizer. It's not that fast, but it's very accurate when it actually goes down. So it will slowly go to a result, but it will not turn back. So I really like that optimizer. I figured out that I actually needed to use a categorical cross-entropy function or a sparse categorical cross-entry function. Any of those works because I have multiple outputs. If you are using something that will give you a percentage or something that it's a binary cross-entropy, that will work. But in this case, I have categories, so I will use either categorical cross-entropy or sparse categorical cross-entropy. In my case, sparse worked better. It gave me a better accuracy, so that's why I chose that one. And the metrics I will look at is the accuracy metrics. I run a fit on the compiled model. I use 100 steps per epoch, and I do 50 epochs. Could have done more, but as I And when I added the TensorflowJS, it actually went back to version 1.15, and I didn't have the right graphics set up, so I actually could use my GPU for the training, and training on CPU is very slow, so therefore I minimized the actual training time in order to get this video ready so I can show you all the steps. And then I have this validation data with 10 validation steps on my validation data set, and then I run a validate after everything just to see that how the accuracy actually was when everything was done. And then I will save this Keras model into an H5 file, and that is something that you can use to convert to any other format. You can convert it to TensorFlow Lite or to any other format if you like. But I also found that TFJS, so the TensorflowJS library, had converters built in to take this Keras model and save it in a directory of Tensor.js, so you can actually use it right off the bat, which is really nice. So if we go and look at my Tensor.js directory here, we can see that we have a lot of group shares, so binaries that we can use in my example here. So it's 17 binary files, and we have this model JSON which describes all that is in this model, so we can actually use it from our web page. Looking at the actual index file here, so the index HTML, it's not that much code. We have some styling in the header just to get the images displayed correctly. I have this script tag here where I get the TensorflowJS, the latest version of that. Then I have my container here with all the cat images, and my prediction I set just working in that div, so it actually will print out working until it actually gets a result. Then I have my predict function here, and I will run this predict function after 1 second, because I want all the images to have been loaded before I actually run the prediction. So the predict function will load my layers model. So it will look for this JSON file that we looked at earlier in my Tensor.js folder. And I run this with just a standard Python HTTP server, so I can try it out. So you can use any HTTP server as long as you get cores and everything like that correct, or otherwise it will not load the model because of you don't have the access permissions to do that. Then I set up a long array of names here. So this is cat1, cat2, cat3, dog1, dog2, dog3, and that's just the JPEG image names that I have up here. So in this div I have IDs of those names. Then I will get the current element with that name, and I will get the pixels from that element. So I will use the TFBrowser function from pixels. So that will give me an example back, and this example does not have any shape, it just has the pixels, so we can use that to run on our model. But we need to reshape it so we can actually use it. So we will reshape it as an image of 300 times 300, 300. So it will have a width and height of 300 because our model needs that. And we will use one batch. So it will be the first batch and the only batch. And then we will predict something and get an output. And we will run this output argmax on the axis, so we can actually get the best result out. And then we run a data sync to get the actual value, and that will give us an array of predictions. That prediction array, the first element of that prediction array, is the actual answer. So we will look at if it's a 1, then we have predicted a cat. If it's a 2, we have predicted a dog. And if we get any other predictions, probably a 0, then we don't know. So don't know I got. And then the prediction is what I print out that there. And that's all the function I have in TensorflowJS in order to read pixel data from an element, run it through my model, get a prediction back, and display the result on my web page. So this was what I wanted to cover today. I hope that you found this interesting. I hope that you learned something today. Perhaps you got inspired to get out and train your own model with your custom data set and see what result you can create with this technique. If you have any comments, suggestions, leave them down in the comment section below. If you like this video, give it a like, share it with your friends and colleagues. If you like tutorials like this, puzzle solving, or other interesting libraries that I might cover on this channel, then please subscribe, and I really hope to see you in the next video.